Imagine a building engulfed in flames in downtown Chicago. A fire truck is firing a massive stream of water up a 10th floor window with absolute precision. Intuition might tell you it's just a big tank and a powerful pump, but let's test that logic. If it were just the tank, a 500-gallon tank would be empty in less than 2 minutes. So where does that seemingly endless supply of water come from? Why would they still connect a hose to a roadside hydrant if the truck is already powerful enough? And how can a machine carry 4 hoses simultaneously? Let simple why answer these questions below. To understand how far water can travel, we first need to discard the most common assumption and our biggest mistake. Most people, when looking at a fire truck, see a giant water tank on the wheel. Modern water tankers typically carry between 500 and 1,000 gallons of water. While that sounds like a lot, a serious house fire can consume water at a rate of 300 gallons per minute. Let's do the math. In about 3 minutes, the truck will be out of water. If the water tank were the primary source, any major fire would be hopeless before the first ladder could be erected. The fire truck's water tank, not as the heart of the system, but simply as an initial lifeline. It gives the fire crew a few precious minutes to stabilize their position while their teammates search for a fire hose. That's right, fire trucks don't win because of what they carry. They win because of the speed at which they connect to, draw in, and multiply water sources. So where does the water actually come from? The answer is the city's groundwater network. However, the process is not as simple as you might think. If you were to use all the water pumps from 20 apartment buildings and channel their power into a single hose, you still wouldn't achieve the power of a medium-sized fire truck. This vehicle isn't just for collecting water, it acts as a mobile pressure station. It uses the same pump and propeller, but what's under that bright red vehicle can push water up to 60 to 70 meters, equivalent to throwing a rock to the top of a tower. A fire truck is a sophisticated predator capable of turning any nearby water source into a high-velocity weapon. It integrates itself into the environment to maintain a relentless flow. In rural areas where hydrants are scarce, the truck's versatility truly shines. It can draft or vacuum water from lakes, ponds, or even a neighbor's swimming pool. But simply connecting to a source is only half the battle. After all, water doesn't magically fly across a street just because it's inside a pipe. To understand why fire trucks can spray water so far, we need to look at the centrifugal pump. According to FAMA, this design is not just an industry standard, but has been the backbone of fire trucks for over a century. Unlike simple piston pumps that merely push water, this pump operates by throwing water away. Inside, an impeller, like a propeller, spins at extremely high speed, driven by the vehicle's engine via a PTO, power takeoff system. Water enters the center and is flung outward by centrifugal force, much like clothes being squeezed against the sides of a washing machine during the spin cycle. This process transforms the engine's torque into a powerful flow. Common PTO pump sizes can deliver from 250 to as much as 1,500 gallons per minute, GPM. For more demanding challenges, engineers use multi-stage pumps to boost discharge pressure from 250 to 1,500 pounds per square inch. This is more than just a vehicle. It is a masterpiece of physics, transforming mechanical energy into a force powerful enough to pierce through fire and rubble. However, even such a powerful monster has an unexpected weakness. which explains why the first few seconds at the scene are so crucial. Centrifugal pumps are masters at moving water, but terrible at moving air. If the pump body is full of air, the rotors will just spin in vain without being able to create the necessary suction. This is where priming becomes the hero. Before the main assault begins, the firefighter must use a small auxiliary pump to suck out all the air, creating a vacuum to draw water into the system. To the average observer, it looks like the firefighter is just standing next to the truck, but in reality, the pump operator is performing a precise maneuver, monitoring the gauges and bleeding to ensure water completely replaces the air. This reminds us that firefighting isn't just about holding a hose, it's about mastering physics under extreme pressure. And once the pump is properly primed, another question arises. What truly determines the perfect curve of the water's trajectory? Is it the extreme pressure or the sheer volume of water itself? When the water finally leaves the nozzle, it's a dramatic balance between pressure and flow. Most people assume that to reach a high window, you just need to add pressure. But in the firefighting world, pressure is just speed, while flow is the muscle. Imagine throwing a tennis ball, low flow, is easy to throw quickly with high pressure, but the wind will soon stop it. A baseball, high flow, carries much more momentum and travels much farther. Firefighters use different nozzle types to shape this relationship. By squeezing the nozzle, they increase velocity. But if the flow rate, GPM, is too low, the stream will break down into a mist before reaching its target. That's why the job of a pump operator is so complex. They had to maintain sufficient pounds per square inch to counteract gravity and air resistance, while also ensuring enough gallons per minute to effectively cool the fire. It was a precisely calculated curve, combining fluid dynamics and pure mechanical power. Once we understand why fire trucks spray water so far and so powerfully, the story becomes even more interesting, because this machine didn't appear out of nowhere. It's the result of hundreds of years of trial and error, improvements, and urban emergencies. To truly appreciate the modern fire engine, we must travel back to the soot-stained streets of 17th century Amsterdam. In an era of timber houses and open flames, fire was a constant, looming shadow. Firefighting meant lines of exhausted men frantically pumping wooden levers by hand. These early engines were little more than oversized squirt guns, primitive, weak, and entirely dependent on human muscle. The 19th century brought a steam-powered revolution. Massive coal-fired steam pumpers roared into cities, offering a quantum leap in power. However, they had a fatal flaw. You had to wait for the boiler to heat up before you could throw a single drop of water. In a fire, seconds are lives. This led to the birth of the internal combustion engine, the ultimate game changer. Today's pumper is the direct descendant of those clunky wooden levers, but refined into a ready-in-seconds powerhouse. It's more compact, more reliable, and capable of a relentless force that our ancestors could only dream of. The very principle that allows this truck to battle infernos is the same silent science serving us in our daily lives, in places you'd least expect. We now realize a fire truck is not just a truck with water. It is a mobile pressure fortress built upon one of the most important hidden machines in human history. The next time you see a fire engine arching a massive stream of water over a skyscraper, you won't just see a giant hose. You will see centuries of engineering, a complex urban infrastructure, and a masterclass in physics working in perfect harmony. One simple fact at a time. That's how we understand the world. Like, subscribe to Simple Why and tell us your question below. Your why could be our next video.